From lunchtime discussion to a NIPS paper. I guess we already went over this one, that some games are more manageable for the agent than other ones, and then why. Another thing is, what other tasks can this agent be applied to? And would the architecture need to be tweaked, or anything you see applied in your own line of work? Another question that I think is interesting is, we start the agent starts with complete random weights. It has no clue about the environment whatsoever. Is there a way to inject some prior knowledge into the agent about the environment? Another thing is, we're using the highest game score as the reward. Could there be other reward functions that we could use here? And then finally, even though the architecture is general and the hyperparameters are the same, still they had to train 49 different agents to perform these 49 tasks. And can we generalize these agents? You know, like when we do image recognition, you know, just chop off the last few layers and then transfer the network to another task. Yeah, these are the questions.
Sorry, I missed something. You say you already talked about the first question?
Yeah. When we were discussing the... Is it working? It is?
It's not?
When we were talking about the... Yeah, thank you.
Sorry.
This one. Right, so this one where the game or the agent really didn't perform at all, so it didn't as well as random play. But yeah, so there could be some other reasons. So in this case, the reason was that the reward was so much, it required such a complex strategy that by the time you get to a reward, if you play randomly, you would have a hard time stumbling upon a reward. But there could be other reasons why that happens, why some of these games are not as good as, like, Pac-Man, for example. We all know Pac-Man, right? So we can discuss that.
I was hoping we would.
Here.
So Pac-Man's an interesting case where it scores like 13% of normalized human performance, and that means it knows how to find hills, it knows how to find the ghosts in evening, but it never ever discovers that it's good to have the ghosts chase you just until you get to the power point, right? And so it's an interesting case because all the elements are different, right? And yet it's so unlike Montezuma's Revenge, where the whole world changes completely in ways that we'll never discover unless those two things grow. It produces all the changes that are components of the ideal strategy for this kind of thing.
Yeah. That's a good point. Yeah.
So why?
So it learns how to, so it gets to some policy which produces some reward, but it doesn't get the policy that produces the most reward.
And the optimal policy can be thought of as, directly related to suboptimal policies that are non-zero.
Mm-hmm.
So how could it discover that optimal policy?
Yeah, I mean, it's a funny thing because you mentioned this example of looking at YouTube videos. I guess for me it'd be really, really interesting if you could get something that discovers a kind of interesting technique, like get the ghost to chase you for a long, long time, take that all four right behind you, and then get to the power. So I read this paper as more telling me which video games are interesting, but which, something interesting to keep learning.
Well, yeah. I think it also tells you something about the strategies that you want to take to different games. Or there are games that allow for kind of simple strategies. Just push the button all the time, right? Or where you actually have to plan ahead.
Yeah. So just one more point. So what makes Montezuma's Revenge and this Pac-Man similar is that so I feel like sparse is maybe not the best term. Both cases rewards are distant in time for optimal strategies, so it's just a lot of time steps.
Yeah, I'm just and there's also sparseness there involved as well, because unless you get there, right? Here you know probably every time you punch somebody, you get scores, so you get reward. So even with random policy, you pretty much soon figure out that it makes good sense to punch somebody. Whereas here we don't stumble upon a reward. Yeah, Jim.
I have a question on the algorithm.
What?
So it looks like it's sampling a mini batch and training while it is playing. Is that how it works? So
Say it
it's
again,
like
please.
training on the fly. So it's sampling from the past
Experiences.
experiences and it's training on the fly and it applies it immediately. Because I saw that training is inside the loop of while we're iterating the T.
In the algorithm.
Yes.
In the algorithm. So
Yeah, what does the otherwise mean?
yeah, you see like Q hat toward the end, Q hat equals Q. That's actually updated within a episode.
Yeah.
Is that correct? So my question is, why train so eagerly? Why not just wait till the episode ends?
Because you don't know how long each episode will take. So as you start, you know, depending on the game, you might be dead pretty soon, right? You just take a few steps and then the agent is dead. It's over. As you learn more optimal policies, this T becomes longer and longer, right? Becomes more greater and greater.
Okay.
So I guess.
So it kind of helps, like if you learn something immediately and then applies it immediately, that helps you survive longer. That's right. If you train on the fly.
Yeah.
Okay.
And then keep the counter somewhere outside of you know. So if the episode resets, you don't reset the counter.
Okay.
Or proceed. And you have a question?
No.
Okay.
More like it's just I think it could be improved because like for the complicated game, for example, if there is an example like learn by illustration, it's just based on the Q-value state. Because the whole thing sounds like, okay, reinforcement learning is very Markov based, which means it's an adjacent state, doesn't it? You don't have knowledge on state. So if your action in the last momentum, Montezuma.
Yep.
Montezuma's revenge.
It goes like so many actions, so that means you have many state changes. Markov won't fit the whole model breaks down basically. So I think I've seen papers that they provide robotic arms using reinforcement learning with demonstration to tie knot.
Yeah,
So the robotic arm, what it does is hold a rope, tie a knot. But with the demonstration, it can learn complicated process.
I think that's what he said about the open AI and DeepMind paper that they trained on YouTube videos of that.
Oh, okay, so they do use that.
And also even with Markov processes, you don't. Yes, you might have an immediate reward after. So you have a state, and you have you pick an action, and you might get an immediate reward. But the whole idea of using discounted future rewards is that you're not taking just the reward from the next step into consideration. So you can actually follow the Markov chain to find that optimal state somewhere in the distant future, or not so distant future, but somewhere in the future where you get this reward. Right?
That's kind of like just an estimated.
Yeah, that's an estimated. Yeah.
Did they try changing the gap between the prediction, the Q tilde you had, and then the Q? Like it's basically the Q network at some point in the past, right?
Mm-hmm.
Did that changing that gap, was that something that they tried, or was it always the same fixed gap?
So hyperparameters that they trained.
Right.
Yeah, so they reset it at the specific intervals.
Okay.
But C
Do we
is a
know how much?
hyperparameter, right?
C is a hyperparameter, but they just fix it. Well, yeah.
Yeah, there's an alternative way to you can reset every step, but just every step, 100 steps back. Because every step you could one step back to copy back there. You don't have a copy this way. Because in this way, there's a bias. Because some episodes close to the reset, some episodes far further than the reset, so it's not equal.
Can you go back to a couple of slides where you have the
What are you looking for? Tell me.
the difference between Q from the previous.
The last
That's going
function.
to calculate the future, but from previous.
This one? Yeah.
So if you were to use, say, increase the steps, so instead of calculating from the current state and then the next step, you could say like, okay, what's going to happen in like 10 steps? Would that help to solve bigger or more complex problems?
So I think what you're saying is what we've been discussing so far is.
So like, if you're S prime,
yeah.
instead of saying S prime of the next step,
yeah.
it's like kind of like the S to the
of the steps, 10 steps in the future. What we've been talking so far about is Q, which gives you give it a state, and it outputs the Q values for all the actions in that state. It doesn't tell you how good that state is. So it just tells you in this state what are the best actions to take, but it doesn't tell you which whether the state itself is a good state to be in. And this is what this picture here shows. These are not the Q values. These are the values of different states. In other words, how good is it to be in each state? And there are.
So what is this related? How do you relate this with the previous equation? Or is there an equation that says, okay, I'm in a good state, or I will be in a good state?
Yeah, there's an equation like this, only for V, which is the value of a state.
Okay.
Yeah, so it's not giving you the Q values for actions in a particular state. It tells you how good a state to be. And there, if I'm not mistaken, the actor critic, there's a kind of approach to reinforcement learning called actor critic, where they have two networks. One tells you the value of a state, and the other calculates the Q. So you have
so you can compare them.
Yeah. So you can compare which state you want to end up in.
What's the value of the state different from R?
The value of the state includes all future R.
Well, capital R does include all future R.
No, capital R. Yeah, it does.
But it's in the previous slide.
Let's see. Go here.
When you say value, R is the return, the accumulated return, so you have a reward.
R is factual. It's what the environment honestly gives you. Value is something you anticipate. In the future, like from the future.
So you can predict how useful such an action would be. You can also predict how useful being in a specific state would be, but they're not actually your reward. Your reward helps you determine how good a certain state or action would be.
You would learn V just as you would learn the values of different states just as you would learn Q. So yes.
So just another. So I think here you just learn the action. What is Q? Like is what
The
should
value of the action.
Yes, it's the values associated with each action in each
So
state.
what action? And there it would be also what state should I be?
Yeah.
And state is usually like where on the map, perhaps, right?
Yeah. So is it better to end up in a state like this, or it's better to end up in a state like this, for example, right?
The entire.
But
Yeah.
doesn't Q already answer that question? Like if you're saying that I'm taking an action that is good, then it means that I'm going through a state that has more value.
I think a precursor to that question is how do they compare? If you add value Like, is action created actually better? Are they shown?
You can, I think, you can do either or. So you can have you can learn which states are good, and then take actions that will take you to that state. So that would be the or you can learn a cue which will tell you, given a state, which action should I prefer.
So you can do gene learning?
If you go back to the definitions, the Q definition is Q.
This one.
Like the definition of Q, if you forget about the ultimate, forget about Bellman, right? Q is a action value, right? It's an action and a state. So it's an expected return for the given action and state, basically. So it's a value, but it's a condition of the state and action.
Current state of action.
Yeah, current state and action.
Given current state action,
Yeah.
what if you take another action, and which results in another state, and then you try to calculate the value of that?
The RT is expected return, is accumulating reward for all subsequent actions.
No, I wasn't asking about Q and R. I wasn't asking about V and R with the state. Well, it's not on this slide, but it was mentioned in it before.
So okay, that's okay.
So that's also a good point. That's true. Because didn't we call Q action value so far?
Yeah.
And why do we call it action?
So, like-
because at the end of like the layer, the output layer is a softmax of your actions.
It's not a softmax. It's just a yeah. It's a I guess linear activation. But it is it gives you the Q values for different actions. Yes.
No probabilities.
Well, I think the reason you can do probabilities, you can do softmax. But I think the reason why you might not want to do softmax is because it's nonlinear, and you might want to compare the actual values of different states of different actions rather than probabilities.
It is the Q value, or the value of Q, not necessarily the probability of action.
Yeah.
So I think what I was trying to get at is the reason it's action value is because all your agent is doing is an act. All you're doing is picking an action.
Right. And you expect some
Given a
value.
Given
Yeah.
state and an action. Right?
Right, yeah.
Yes.
Yeah.
But if
Well, no. Given a state, what is the value of all the actions that you can take on that state?
if you go to the equation, please. Right.
Current state and current
Like,
action.
But given.
you remember the concept, right? So the input was one image, the state, and the output was all the Q values, right?
Yeah.
For each action.
For each of the actions, right?
Yeah.
Q value.
So you input an image, and then the output is just these values for different actions.
Hold on.
Each of the
Something
actions.
doesn't sound. So
So there's one value for each.
but
action.
Yeah.
What's the question?
So-
Lost track at this point.
So if you go to the equation, second line, you have expectation of blah 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 at the end given state and action,
Yeah.
which I assume are the previous or current state?
Current ones.
Current state and action.
And S prime, A prime are kind of like what if.
Sure, the future.
Yeah. So that's the next ones.
Yeah. So that A is for the action, is for a set of action. That A at the end is is it a set of actions that I would take at this moment, or is it the actions
This is the action
that
that
I've
I-
taken previously?
This is the action. I'm in a state. I take some action, and I anticipate that I'll end up in some other state.
The next.
And then
From,
the next
from which you
state,
can do A prime.
yes, from which you can have some values for actions there.
Okay, so it is.
So it shouldn't be like you take an action which results to S prime.
Yeah.
Yeah.
A resulting S prime.
Yeah. So you are in S, you do A, you end up in S prime, from which you can do A
take.
prime.
Well,
But then,
Oh.
but then I think
Oh,
the
okay.
conditional sort of presentation doesn't sit well with me, because usually, like in hidden models, when you say given, that means that's past, that's history. But I think there is something in between that S and A, that there is a sequential nature between that S and A after the given sign, right? So you're saying that either you're in
so what you're saying is that we arrived at some state, and then at some point later we take an action after we arrived at that state, right?
Yeah.
And then at some point later we arrived at a different state, right? So how do we capture that?
Because it seems that S and A aren't concurrent. Apparently, you're in S, you do A, you end up at S prime, right?
Yeah.
I'm just saying that notation doesn't capture this.
Yeah.
If that
I
makes sense.
mean, it's like
Right.
you can think about it as a space, like in a space, S and A is just a vector. S is the beginning of the vector, and A is the direction of the vector or something. So like they're sort of together. They're one.
Like I think of this as space. You have like position and velocity
Yeah.
defining a point. So if you know the position and the velocity, only then can you predict the next time step. So the point is represented by both S and V. So
Can I
that's
draw?
so-
Yeah. The fun starts when you actually, you know, it's not when you start thinking about the reward, right? Is it the reward that you get, like, if you start talking about notation, then is it the reward that I'm getting at this time step? Because I'm in a state, I take an action, and you know, this reward should be R prime, or because I'm getting a reward after I've taken this action. So like, there's that.
So
Like,
we have,
if I confuse you more.
we have only 5 minutes. Can we go back to your discussion points, because we didn't talk about anything?
You're absolutely right. From this state
I'd
to
like to
the
do
next
that.
state, I'm taking this. That's my maximum.
Yeah.
Yeah, and then for my next one, my possible actions again.
Would be a set.
Huh? Yeah, so it would be, again, what are you choosing if it's maximum, right? It would be whatever the maximum reward you're getting, right?
Yeah.
It's the same thing. It's not concurrent.
Yeah.
Yeah, sequential.
We'll talk about it offline. I'd like to hear your point
Yeah.
about it.
I don't understand your fourth.
1, 2, 3, 4. Yeah, so basically the way and actually that might be helpful maybe here or in the Pac-Man discussion. So what we're rewarding the agent for, we're just taking a raw score. And excuse me, the reason why, or that might be the reason why the agent performs so poorly here, because it doesn't see a reward for a long, long time. So if we use some kind of other reward function, for example, if there was a way for us to tell, oh, this guy in the head is getting closer to the key, that might help.
Novelty might be another one where if you can produce
Yeah, exactly.
a pixel arrangement that's maximally different from a previous pixel arrangement, then that probably is helpful for exploration
Right.
and suggests maybe higher possible rewards. So it's like a proxy maybe.
But by doing that, don't you kind of inject your own assumption how you should play the game into the strategy? So like, shouldn't reward be something that's kind of always strict? That's always something that the environment gives to you.
Well, if you look at it,
You can always define that reward.
if that's the game, right? If I'm playing it and I know that I need to get the
Success of your
Okay. No, I'm not saying it's not reward for this. Okay.
Well, if you look at that game and if the goal is to get that key, if you're a kid, you probably, if you walk closer to the key, you would know that you're closer. So that's some sort of reward. You'll be happy if you want to jump over that, I don't know, valley, whatever it is, and you do that successfully. You're like, yay. But the machine isn't. Like, that's not present in.
But the reason that you as a kid would know that is that's another discussion point that you have, is that you're
you
comparing
want
that.
to get the key, but the agent doesn't know that.
No, for sure. But you as a kid who's playing that game knows that you want to get close to the key from your prior experience, like you played other games, and that's how it works.
Well, it
when
probably
you write
says
that.
at the beginning. You want to get the Otherwise, I'd be just confused.
It's modifying the feature.
Actually, you can always redefine a reward function. Like you go to rope first, that's good reward, right?
That's actually interesting. You should do
You can always
NLP
define
combine.
that. You have to, you go to rope first. That'll give a reward.
So some kind of stage rewards, right? So
Yeah,
getting
so
but then you would be injecting like really, because you get to the next level, right,
Right.
which will be completely different, and there getting to the rope might actually get you.
But that's a good point. If one of the screens in a game is telling you like what you're trying to achieve, maybe you can add that as your reward function. So
I
last
never
question.
played the game, so I don't know how is there timeouts? Would it ever learn at all before like timeouts? Like,
Here?
yeah.
No, that was
No, that's
0%.
the whole point. That it it just plays like randomly.
just like-
Yeah.
Why? We finish the game or why? Like,
It just dies before just gets So there are situations here where you would die
oh, I see.
if you get eaten by the skull, I think, or if
Oh,
you
I
jump
see.
from
Or the
if you jump from
feet
here
burns.
all the way down here, you're gonna crash and you die. So there are there are situations in which
There are more ways that you can die than you can get reward. By which you got an 830 and therefore
The Maluba paper where they solve Pac-Man?
Oh,
Anybody
you did?
read the Maluba paper where they solve
No.
Pac-Man? Yes, it might be interesting. to
Is that
follow.
2018?
17, I think.
17?
Yeah.
Would you like to talk about it?
I can give you one
Oh.
sentence. So this,
Not today.
They hand coded it's because this comment reminded me they hand coded an ontology. So they tell it about ghosts, they tell it
Right.
about fruit, and they tell it about power pills. Just they give it the ontology. They say
That's fine.
consider the role of these objects in the reward function. That's enough.
Well,
So are you around on December?
If I'm going to talk, it'll be about NLP, not about.
oh,
SASE.
okay, good. That works too.
We like NLP too.
Okay, that's too much friendship.
Pressure is good. All right, thanks, Nick.
All right.
Yeah,
Thank you guys.
thank you.
Thanks a lot. Thanks for staying.